trees are just an abstract data type. And what it is, so we go back to the concept of our nodes from our linked list. Those are the same type of data we're dealing with. We're dealing with nodes. And so it's similar to a linked list, but what's unique about a binary tree is that it isn't linear. So linked lists are linear, kind of like an array. You know, there's sequential. Binary trees are not like that at all. With binary trees, we have a previous and a next, or a predecessor and a successor terminology you want to use. And so the tree itself is just a hierarchical relationship between all the different nodes. And so your nodes can have numerous successors, which are children, and the predecessor is its parent. So the very top node is called the root. So instead of using the word head, we would actually use root for that very first node. And because there's only children dependent upon it, but there's nothing above it. So the root itself doesn't have a predecessor. So every node in our tree can have children, but they don't have to. So when you have a node that doesn't have any children, they're called leaves. And any node that's not a root or a leaf is an interior node. So you got to think about like an actual physical tree where it has no roots that are in the ground. There's only one root system for a tree, right? And then each one of it has its different branches, and on those branches we have our leaves. And so the overall height of our tree is defined to be the length of the longest path. So the length of the longest path from the root to a leaf in the tree. And so a tree with only one node, the root, has a height of 0. So here's just what a tree would look like if it was laid out, where the first value of 2 is the very top is our root. And then as you see here, remember a leaf where it has no children. So when it stops is here, and there's nothing succeeding it, then that is a leaf. So that value of 2, the 5, the 11, and the 4, they're all called leaves because they have no children. And then here, our value of 7, 6, 5, and 9, they're all interior nodes. And the reason why they're interior nodes is because they have at least one successor after them. So here, no successors, so that means that it is a leaf. Here, it has a leaf. On the 7 has 2 successors. Over here, your 5 has 1 successor. As long as there's at least 1 successor, then it is an interior node. Okay. Question? Yes. Sorry?
Because there's 2 bodies.
There's 2 bodies. There's a body over here.
Yes, yeah, that's what I was wondering.
Yeah, it really shouldn't use repeating numbers if we're trying to explicitly show let's guess it. Well, technically, it kind of does. You think about it from an inheritance perspective. So 2 has the parent of 7, which, well, that's a horrible example. Let's try it. 4 has a parent of 9, which has a parent of 5, which has a parent of 2. But as far as arrows, would 2 arrows be pointing at the value 6 at the same time? So could 7 and 5 point at 6 at the same time? Not from a binary tree perspective. There is that format, there is that layout where there is potentially 2 parents to 1 node, but it's not a binary tree. Yes.
According to the tree there can't be any looping edges in that. So I'm not sure if that particular would be a tree, but it definitely will be a binary tree.
Okay. Yeah.
It depends on how you're trying to find it.
Yeah. Yes. It depends. So that's whether or not there's sorting involved. So let's look at the different types of binary trees. There's not just one type of binary tree. This is just a first image of a binary tree, but there's more specific data associated with it.
Is it only just the
Would 7 be a parent, or is this 6 is a parent?
6 is the parent, because when we look at the node struct, there's only one previous and one next.
Okay, so there's only one previous.
Yeah. So this is the thing about binary trees. Each node can only have 2 children, a left and a right. Okay? So there's different types of trees we're going to look at. This one is specifically a binary tree, because if it has 2 children, 2 is binary, right? At least last time we checked it was binary. Okay. So each node can have no children, 1 children, or 2. So those are your options. And then any child can only have 1 parent. So if you're doing a binary tree, it can only have 1 parent. There is a different type of tree that has the ability to have multiple parents, but not in binary. Okay? So there is a distinction between trees and binary trees. Does that make sense? Okay. And so here, we use 2 pointers so that we can identify our left and our right. And so this is an example. So you always have your root at the top, and then this one here has 2 maximum children. This one here on the left is a leaf. So the left node is a leaf from this one. Why is this a leaf? So that's no children. So over here on the right part of the tree, his child has 1 child and 2. This is where they're not binary trees. So getting to your point here, this node potentially has 2 parents, but that's not binary. Okay? Because they only can have 1 in binary. And then this here, because it has 3 children, that's not binary. Because binary is 2, 0, 1. Make sense? Okay. So, this is called a full binary tree, and what that means is that every node other than the B's has at least 2 children. So here, A has 2 children, C and C. B has 2 children, C and D. D has 2 children, C and A. So they call that a full. So every node other than the B has 2 children. So we don't have any example of, there's nothing that's part of this tree that doesn't have, there's nothing that's in this tree that has just 1 child. So as long as it's balanced with 2 children per node, or a leaf, then that is a full tree. Yeah.
Almost like you think of a contact mutation.
Oh, yeah. Okay, so here, so look at the difference between the 2. This is a complete tree. This is a full tree. A full tree says that each node, except for its leaves, has 2 children. When it comes to a complete tree, every level, and we'll look at another image here that talks about the level, every level, except the last one, is completely filled. So all nodes are as far left as possible. So this one here, you see that because this node C doesn't have 2 children, that's what makes it not a complete tree. Does that make sense? This is a complete tree. And you see how this one, there's 1, 2, 3, 4 levels, but they're not balanced. Okay? This one here is balanced. You see how we have level 1, level 2, level 3, level 4, and they're all filled out. So we have a left and a right for each node, and then they all end at the same level. Yes, sir?
Does it need to be balanced out in order for it to be considered complete?
To be complete, it just means that all the nodes at every level are filled out. Completely filled out. So at level 3, each one of those nodes at level 3 has 2 children. Did that answer your question or not? You sure? Okay. Yes, sir.
So 7 through 14 would be
Yeah, all of these are used because they have no children. Is anyone tracking on that? So when you're talking about what levels, so I completely just lied to you, the last statement. It starts at a value of 0. Or computer science, right? So it has to start at value of 0. We don't start counting at 1 unless we absolutely have to. So here, the root node is level 0, the next level is 1, the next level is 2, and it just increases by 1 sequentially for every level that you create children from. Now, if we're talking about big O of a binary tree, how do I know which one of the orders I would use in a binary tree? What do you think the answer is? Remember the different orders? Right? So I'm trying to get you to correlate previous knowledge with current implementation because they do all roll together. There we go. Okay, so these are our common orders, right? And we have the slides afterwards that define which one. So which one is this? Binary. So for every level it gets half. So for every level that it gets half, which big O order do we use with halving? We talked about this last week. I think I heard it. Yay, log. Just think about it. Binary tree, you make logs out of trees, right? Look, I'm telling you, this shit works. You're going to get to the exam 3 or your foundation and say, oh yeah, Professor Whiting, her logs and trees. Yeah, I got it. It's log n, okay? Anything is half. Doesn't that make sense? Come on. I show my JavaScript class. I'll show you something really silly. And I do it with them too. I gotta tell you, whatever it gets you through the classes, that's awesome. Okay? This is kind of funny. Silly, but funny. I think this is it. Okay, so when you're dealing with arrays in JavaScript, there's 3 different types. Oh, here, there's 3 different types in JavaScript. There's regular, condensed, and literal. So this one here is a literal array because you don't use a constructor that says new array. Now it's look, does that little square bracket there almost look like an L? Right? So the L is for literal. They all just groaned at me. I'm like, you're gonna know that shit on the exam. Because it was stupid. They were like, oh my god, I forgot. But you'll totally remember it. So I don't only torture just you guys. I actually torture all my classes employees. Okay, so when you're doing binary, anything binary is log n. Okay? So if we have a binary tree, then the appropriate big O order notation is log n to do the math. And so here, our total number of nodes, and in a complete binary tree, here's your fabulous equation. Because God knows you can't do anything to your science 1 without equation. So, when we were talking about recursion, you know, when we were trying to find out the max number of iterations, and we had a little formula. So here, so how many, what are max number of nodes in the tree? Binary tree, you would use H2 because it's binary, right? And the loud stuff is actually lining up and making sense. And then H is your height, plus 1, and then minus 2. Why would we do plus 1 to the height? Yes, because it's like 0. Awesome. You guys are killing it today. Pretty good for a Monday, huh? And then we do a minus 1 to the max, okay? And then here, the height of the tree, log n, right? Alright, so we have a little log x. So you have 15 nodes. You want to find the height of the tree. You do your log x. So your maximum divided by 2 equals the log of 8. So your height of our tree is 3. So if we count it, 0, 1, 2, 3, it matches. Right? Because it's 3 minus 1. Remember? We start with 0. So that's how we end up with maximum. Equation. Alright. So from a visual for a second. Hey, Jonathan, you're not even paying attention. He's like, look at shit. I already know this. I know better than you. All right. So from a visual representation, this is where we have our data itself. And so in the previous examples of all of our nodes, when we're working with linked lists, we always just had our next, right? Well, now we have a previous as well, because we've got to know who our parent is and who our children are if we have any. Does that make sense? Okay. So here's just like a basic constructor for our tree node. So we have our data, and we used to have just one pointer for our struct. Now we're going to have two. All right, binaries. Everything binary is two. Just keep thinking about that. And it's a tree, so there's logs. All right. So your binary tree, it has this natural implementation, and then we have our nodes will have a left and a right. And so you need to be able to reach both of those pointers. So how do you traverse this guy? Because we can't just look for null, right? Because we're going to have more than one node that potentially has a value of null in it, right? Because we have leaves. So we have multiple ends to our binary tree. So when we're doing linked lists, we knew we found the end because of what? What was the value of the next pointer? Null, right? Well, we can't apply that here because it's like this. We have a whole bunch of different ends. All right, so how do we deal with this? All right, so there's actually three different ways of dealing with traversing your binary tree. You can do pre-order, in-order, and post-order. So what the heck do they use? Well, first we got to look at our tree traversal, which is choosing time. You're like, holy crap, how much more complicated is this? All right, so when you're talking about depth first search, you think about depth. You're diving, you're trying to dive as deep as you can. You're just going straight down, right? Like, maybe like snorkelers or scuba people, you dive and try to get to the bottom, right? Having all that gear so you don't have to stay to the top. So we want to get down to the bottom as fast as possible. So that's what a depth first search does for us. And so when we do that, we're gonna check all the way down to a leaf before even backtracking and exploring any other path. So with your depth first, we're going to find out where we can get to the very bottom as fast as possible. So here, we're going to look at A. A has two children. But we're going to do the left first. You'll see that with binary trees. We always do left and right. All right? So here, we do the left first, and so we get the B. B has two children. One is D, and one is E. When you check out D, it has some children. D ends up being a leaf. But, so we've got to check out E to see if E has any children. E has children. We have an H and an I. But we go left first. Binary, we always start with the left on binary. Okay? And then here, so we go from E to H, and then we check out H, and then H is not really a valid binary tree. Why?
Three children.
Three children. So that's really wrong, isn't it? We're just talking about tree traversal. We're not talking specifically binary tree traversal. But it still works the same way, okay? So in this example here, this is not a binary because it has three children. So it's really important you understand the distinction. Keep thinking about binary. Binary is 2, 2, 2. That's all we care about. All right, so when we keep going down, 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 so we find where none of the children have any more children. So when we get to the point where everything is finally a leaf, at that level we got to, we call that depth first. Yes, sir? Oh, that makes sense, though.
Yeah, no, because there's some things when we're trying to play and do algorithms back where we know that the height of the tree is we're going to be sitting there all day trying to figure out why it was here.
So, Jonathan is sharing with us very valuable information. So, if you're trying to calculate an empty tree, so the height is 0, right? And you do your -1. We're going to end up with a -1 for an empty tree. There's nothing in it. You got it. So, what is the value of your root node? 0. So, it's not 0. What's that? We're we're solving for the h. So if this part of it is 0 because we have nothing, you end up with a -1, right? The 0 minus 1 is -1. Is that true? I think it is. I'm getting nothing but silence. I have a voice shot for that one. That one's pretty fun. Okay. Alright, so this is depth first. You just go as deep as you can all the way down. So specifically on binary trees, alright, you have a depth first binary tree. You have pre-order, in-order, and post-order. And they are chosen based on how the root node is visited. So the root is in charge, is the parent of all. So, just think of the dictator parent, it's like, I'm in charge, you will listen to me. Alright, so the root says I'm in charge. So when is the root node visited? When you do a pre-order, the root is visited before. Pre means before, right? Does that kind of make sense? In order, the root is visited between the subtrees. So you think about in order. And then post-order, the root is visited after both subtrees. So if we're looking at this example here, or not. So if we did a pre-order, this example is I pre-ordered depth first. Why is it pre-ordered depth first? Based on this statement right here. Why is it pre-order? What I just say, when is the root visited? In this example here. It's first, right? So this is a pre-order, right? Because we're starting with A. Alright, so there's a function for pre-order. And what it does for us is the root is visited before it's left and it's right. So for example, the visiting of a node is represented by printing that node. So here's code for a pre-order traversal. So here, the root is visited before it's left and it's right. So the order would be 8. These are going to be fabulous exam 3 questions. Really would make sure you understand that. So another example of a pre-order traversal, if we include more children to the nodes. So we do A, then B, C, and then D, E, F. Right? No, I'm sorry. A, B, C. No, C. Okay. Because we always do the left before the right. Oh my goodness. Okay. We always do the left before the right. So here we do our A and our B. Because B has children now, you have to finish the leftmost. B first, remember? So then it's D, and then D goes to G, and then G doesn't have any more children, but it does have one at the same level, and so that H is visited. So that rolls us back up here to B. So then we have to do our E and our I, and then once we hit the leaf on that guy, then we can do the right side of our binary tree, and that's C, F, and J. So remember, the binary trees start with the left, and then we go to the right. So the in order, this is where the root is visited between the left and the right tree. Alright, so for the following example, the visiting of a node is represented as an idea. So this is the code for in order. So what happens here is in order, the root is visited between subtrees. So B and C are subtrees. Are you tracking? So those two subtrees get evaluated first. So then the node, so we do the B, the A, and then the C, because it's in between your two nodes. So if we had a more complex one, so here's our A, but we're doing in order, so we actually need to visit the roots first, right? So we come here to B, B has children, so now we still have to go even further down. So we go based on the children of the leftmost branch. So D has children. D has a G and an H. So if you apply the in order traversal, D technically is the root node for G and H, correct? You see that? Or just, like, don't even think about the rest of the tree. D is the parent for G and H. So to traverse that in order, you would have to go GDH. Make sense? So then we come up to our next node, and we have a B's. So we just did D, because we did G, D, and H. B is in the middle of D and E, correct? So if we look at D and E, then the next thing we have, so we go G, D, H, and roll up. And then our B, because that's in the middle. So there's our B. And then because E doesn't have two children, only has one, then we can go ahead and do our E and our I, because there's nothing here to visit on the left. So that's why it goes from G, D, H, leftmost, in order, H. Okay, so leftmost, in order, E, leftmost, nothing there, skip it, I. Then we come up here, now we can finally do our A. We come down here, C has a child on the left and F has a child on the right. So here, there's nothing there on the left, so nothing is going to be printed before our F, because there's nothing there. Then we do our F, and then we do our rightmost child, which is J. And then we can do F's parent, which is P. How many people I just moved on that one? Yeah, okay. So when you're doing this in order, you do it in order at the lowest level. Okay? So, who's comfortable with this one? Totally get this one, right? In order. So you visit between the subtrees. My subtree is B and C. Good? Yes? Okay. So then the root gets visited between the trees. And you always start at the left in binary trees. So my left child is B. The root is A. My rightmost child is C. If I do them in order, which means that the root is visited in between its children, so then we have our B, then the A, which is the root, and our C. Does everyone get that part of it?
I'm just curious, when you say visited, you mean you're checking the data of that node, or you're actually going through that node? Because, like with the pre-order version, your main link is the root node, so that you pass that in, and it runs through the recursion. What point are you passing in? Which node point are you passing in the initial starting point?
The parent.
Okay, so you are still starting with the root, you're just not checking anything.
Right. So this is the code. If this is representing the root, or the head, right? So the guy that is the pointer to the beginning of the memory. When we do it in order, we go to the left child first. Left child first. And then we go to the right child. Here's our right. Okay, so if we take this concept right here, and we apply this at every level. So if we look at this tree, so if we're doing an I'm totally going the wrong thing. How about page down? Page down is so much better. There we go. If we're going in order, which means the root of each level is visited in between the left and the right child. So we understand that B would get visited first, then A, and then C. Good? That part of it you're fine with, right? Okay. From a visual perspective, ignore the fact that A is there for now. Go to your left. B has two children. Yes? It's D and E. Okay? So we have to examine those next two nodes. Go to the left first. D has 2 children. Right? And if we do that in between, apply the same concept of EAC, except do it here with G, H, G, D, and H. Alright, so this would be B, that would be A, and this would be C. Does that make sense? Just take one small chunk at a time, one parent node at a time. Okay? So just ignore the fact that we have all this other trees for now. If you're dealing with just these 3 right here, there's one parent and these 2 children, what order would we visit those at? In order. We're doing an in-order traverse. And in order means the root is visited in between the children. From the left. Remember, always go from the left. That's how we read in English, from the left to the right. My first child is just these 3 guys right here is G. Its parent is D. And the right child is H. Okay? So, we're taking this previous example here. Same thing. And we're just applying it right here. So, just do it in small pieces so that you don't get overwhelmed. Okay? So, we got to the very bottom because we're doing that first. So, my first 3 are G, E, H. Does that part make sense? Yes? Okay. He's the leftmost child of group D. Correct?
Not understanding.
Okay, that's fine. So, look at just B, B, and E. We're going up one level of our notes. Alright, just so if I was going to visit D, E, and C, what order would they get visited in? D, E, and E. They all sound the same, right? It's kind of hard. You're dealing with just 3 of them. It would be D, B, and E. Yes. Break it down into a parent and its left and right. Is everyone tracking on that part? So, we started out down here because we went depth first. So we went as far to the left as we could get. So our first 3 to do in order traversal is G, D, and H. Okay? Anyone not good with that? Why?
So whenever we're reading trees, it's not from top to bottom, it's left to right.
Yes.
And that's every time.
Well, yes. We're doing depth first. So remember that depth first. We're getting as far to the bottom as we can, starting at the leftmost node.
And once you read a node, you don't read it again, right?
No. Once you've visited that node, then you're done with that node.
So, and that's just for depth first searches?
Yes. Well, no, that's not true.
No.
Wait for that. Let's just focus on this one piece. Okay. So, we're trying to deal with this with just 3 nodes at a time. Slice this off. Just look at this 3 nodes. This parent has 2 children, G, D, and H. And this is as far as we can go from a depth perspective. All the way to the left as far as we can go. So we deal with these 3 right here. And the order that they get visited are G, D, and H. Okay, so we're done with that. So D is the leftmost child of D, B, and E. See this? Just look at these 3 right here. Just focus on D, B, and E. Have we already visited D? Yes. So we're done with him, right? So that means we can come up here. We already printed out our D. We're done with him. So we need to do our B, because our B is in the middle of our 2 branches. So once we're done with this guy, we can come up here and print our B. Our rightmost is E, correct? So we can print that, because look, if you look at E in and of itself, does you want to apply that concept, here, in between the B and the E, is that nothing for that left child that's not there. Right? Because if he had a child right here, we would do depth first, and we would go left, and then print our E, and then our I. Right? We're doing those three nodes. Just think about from those three nodes perspective. If we had a child on the left of E, just like we did with D, it would go D, D, H. Correct? Do you have anything here that would get printed first? The left is printed first. What's here? Absolutely nothing. So I printed nothing. Okay? Does that make sense? So the parent node gets printed next. Here's my E. Then my right child. Here's my I. Yes, sir.
So you're saying if I were on the left, you would have BI?
Absolutely.
How is the system know on the right or on the left?
That's what our pointers do for us. That's the definition of our pointers. See? Our node. We have a left and we have a right. It's how we define our data is how that happens. From a computer programming perspective. Okay? Okay, so leftmost, deep first. The parent is in the middle of the left and the right. D has the left and the right. And is as far down as we can go. Is G. So the left is printed first, or G, then the parent, the D, and then the right, which is the H. D is a child of B. He is the leftmost. We've already printed him. It's been visited, so we're not going to deal with it again. We've dealt with D from a left child perspective already. So now we can print our B. We can print the guy in the middle because we're doing it in order traverse. So we print the parent. So then we go to our rightmost child. Our rightmost child is E. If he had a left, because you drill down as deep as you can, right? If I had a left, he would have been printed first. And because we're doing in order, we do left, parent, right. Correct? But there's nothing here. There's nothing to print. That's why it goes from B to E. Because there's no left child right here to print from E. So then we can print our missing left, our parent E, our child I, because you do the right. Now we've done the whole left side of A. Because we just dealt with all of B. So because we've just dealt with all of B, then we can print our A because we're doing in order. Now we got to print everything on our right. Okay, so now we're dealing with the rightmost child. So we come down here. C is a parent. It has children. It has a left child called F. F is a parent. It has a child called J on the right. So if we had something here, we would have printed that first, correct? Because we printed this one first. We printed this one before this one. We printed our B before our C. Okay? Just apply that same logic at each level. So here, on my left, on my right, F does not have a left child. So I am printing that out right here. Because I would have gone from my A to my center. Now I've got to go depth first all the way down to the bottom on my C. And start from the bottom and go up. That's what we did over here. We started from the bottom and we rolled up. We need to start at the bottom and roll up. F has no left child. It is empty. It's not there. So because I printed my A, which is in the middle of my B and my C, and now I've dug all the way down, find the bottom or the lowest level of my tree, I want to print my value. There's nothing there. So I'm printing nothing before my F. My F is my parent, so I print him because we're doing it in order. And in order says I print my left, my middle, then my left, my parent, then my right. My left of F has nothing, so there's nothing to print. Now I print my parent, which is my F, and now I go to my right. My right is a J. So now that I'm done with that, because C has a left child of F, but it has no right child. So now I've dealt with my F, my left child of C, and so I can print my C, my parent node, because he's in the middle. He's in the middle of F and nothing. You see that? So envision each one of these actually being a complete or a full tree. Okay? A complete tree where each node has two children. This child is empty. Just think of it as just not there. So when you print it, you print nothing. So that's awesome. So here, I can print my C because he's the parent. I've already dealt with my F. And then if I had anything to my right, I would have printed that. Did that help at all? I still lost people. Not that you're willing to admit, right?
The only thing I get confused about is the AFJC part.
Which part?
AFJC part.
Okay.
What I'm trying to understand.
So when you do that first, and we're doing an in-order traversal, A does not get visited until B, then A, then C. Okay? But this is not the only level I have. We're doing depth first. So B has a D and an E. They both have children. D is our leftmost, and so we look at their children, at his children. He has a left, which is a G, and a right, which is an H. So if we get it in order print, we go G, G, H, right here. Okay? Yes. This is the leftmost node of B. So we can print our B. Okay? Because when you do it in order, you print your B. The parent in the middle of these two branches. Right?
So
Because E does not have a left child. There's nothing to print. So that's why E follows. If he had a child, if it was K, we would have printed the K, then E. But there's nothing here. So we don't have to print anything. So we can go straight to the parent and print the E. And then we do his right. Because that's how you do an in-order traverse. The left parent, correct. So we've done all this here. So we're done. So we do our BEI. Because there's nothing on the left here. We dealt with this left. We're done. Now we can do the middle. Now we're back to focusing on B, A, and C. We've done everything with B. So we can go up to the root and print my A. Because it's in order. So we're doing B, A, C. This is everything right here is a successor to C. We've dealt with all. So now we can do our parent, our root. My C gets printed in the middle. And now we go to C. You print it after you've done your depth first. So here, like C has a left. You gotta go down to do the left on the C. F only has a right. There is no left. So if there was one here and it was K, all right, we would have done an A, then a K. Because we did leftmost of the lowest level. But there's nothing there. So we would do our left, then our parent, then our right. The left is nothing. This is the parent F, and this is our right J. We've gone depth first. We're done with the lowest level here. Next thing you do, so if there was one here with an F and a K, you do F, then the parent, and then the right child.
that's why the CBA goes and do it.
Yes.
Just like we do with the
Yes. Yes. But there's no right on this one, so we're done. Okay. I have 20 after 10, so we will talk more about this on Wednesday. There is